This is Module 6, Section 1.3. In this section, we're going to talk about variable expressions, solutions of equations, translating words into symbols, and we're going to have a review of inequalities that you would have covered in Math 900. Variable expressions. In order to get through this section, we need to understand some of the terminology that is going to pop up from here on out in algebra. So starting with the term variable, a variable is a symbol that stands for various numbers. Usually a variable is an unknown number that you're trying to solve for in algebra. And a variable can be represented by any type of symbol you wanted to write, but variables normally in math are lowercase letters, alphabet letters. Probably by far the most common is the lowercase letter x for variables, but it wouldn't have to be an x. It could be any lowercase letter, x or z or a. And it really doesn't have to be letters. You know, if you really wanted to draw a little tree and let that be your variable and solve for the tree, you could do that too. But in algebra, normally you see the lowercase letters. And again, they're symbols for numbers that you normally don't know, or symbols that can stand for a variety of numbers depending on the application that you're looking at. A constant, on the other hand, is a symbol that stands for a constant fixed number always. So again, the most common constants that you're most familiar with are simply numbers. For example, the number 5 always stands for 5 objects. It doesn't stand for 4 objects today and 3 objects tomorrow and 5 objects 3 days from now. It always stands for 5, and so it is a constant. So any numeral that you want to write, whether it be a whole number or a fraction or a negative number, they always stand for the same quantity. And there are also constants that have symbols that aren't numbers. Again, probably the one that you might be most familiar with from math would be the symbol pi, which is used a lot in geometry. Pi stands for an irrational number that is a non-repeating, non-terminating decimal. It always is the same number, but because that decimal doesn't stop and it doesn't repeat, mathematicians decided to give it a symbol so that it was easier to refer to and you didn't have to have rounding error every time that you talked about it. And so they did come up with a symbol for that constant. So it's not just numbers that are constants. That brings us to a variable or an algebraic expression, which is a combination of variables and or constants. It doesn't have to have both. It could have just variables or just constants that are combined with operations, addition, subtraction, multiplication, or division. The thing I want you to notice here is there's not an equal sign in an expression. Once you take an expression and you put an equal sign in it, it is no longer an expression, it becomes an equation. So there's a subtle difference between expressions and equations, and a lot of times that wording can help you decide what the problem, if you're doing homework, let's say, or doing a test, is actually asking for. So some examples of algebraic expressions might be this. 3x plus 5. Now notice that in this particular example, first of all, there's no equal sign. That's the key, that it's an expression, not an equation. There is a variable. The variable is x. There are 2 constants. The 3 and the 5 are constants. There are 2 operations in this problem. There is multiplication between the 3 and the x, and there is addition between the 3x term and the 5. So other examples might be 4t squared minus 9. Again, notice no equal sign. There's a combination of constants and variables there as well. x squared minus 6xy plus 9. That would be an expression, again, no equal sign, negative 1/2 xy. You might have something just like negative 5. Notice that's just a constant. It's not a variable, but it's still an expression. Okay? You might have something like x plus y. Now there are no constants. Those are just variables separated by addition. So now we're going to talk about terms. Terms are constants and or variables. Again, there doesn't have to be both, but often there is, combined with multiplication or division only, not addition or subtraction. If you have addition or subtraction, then you will have more than one term. Okay? So a single term might be something like, for example, 5x. Notice there's a constant and a variable there. The operation between is multiplication. 1/2 xy. Again, there's a constant there. There are also variables. You can think about that fraction as division, because a fraction is just division. 1/2 is the same as 1 divided by 2. So in that term, there is division and there's multiplication. There's no addition or subtraction, so that's all considered a single term. 3a divided by 2. That would be an example. Negative 9. Notice there's no variable there. That's a single term. And numerous other examples that you could write there. The key there is the separation is all multiplication or division, no addition or subtraction. Then there's the term coefficient. The numerical factor or the number in a term or the constant in the term is considered the coefficient or the numerical coefficient. For example, if I gave you this term, 3x, the coefficient in that term is the 3, the numerical coefficient. If I gave you the term negative 1/2 yz, the coefficient is the numerical piece of it. So the coefficient is the negative 1/2 in that term. X squared y. Okay, let's talk about those terms that appear to have no constant piece. You would agree with me that you can take any number, let's just say 5, since we're most familiar with constants and instead of variables. I could take any constant and I could rewrite that as 1 times that number, and I would have the same thing. In other words, 1 times anything is itself. So if you agree with that 5 is equal to 1 times 5, or 10 is equal to 1 times 10, then you should also agree with me that x should be the same as 1 times x, because 1 times anything is itself. And so coming back to this example, x squared y, although there's not a visible constant or coefficient attached to that, you have to understand that if there's no coefficient visible, there is an understood 1 in front of it, because 1 times anything is that same value. And so in this case, the understood coefficient of x squared y is positive 1. If you just have a constant, for example, let's say I said, given the term 5, tell me what is the coefficient. Because there's not a variable piece, then it's only the constant that's the coefficient. So the coefficient there is 5. Okay, moving on. We're going to review orders of operation. Orders of operation was covered in Math 900, so the modules before you started this course. Nearly every student who comes into math has seen orders of operation at one time. They're taught very early in school, but unfortunately, students often have orders of operation confused. They've at some point gotten into really bad habits, and it's ingrained in them and has been ingrained in them for years, and they have a really hard time breaking those bad habits. So it's very important, even if you think you understand this completely, that you practice enough of these that you can make sure that you're getting the answer that the book or that the review problems are giving you, so that you make sure you don't have any habits that are wrong that you've been doing for years. So most people have learned orders of operation with some sort of trick. If you look at the bottom of this particular page, many people learn the phrase, "Please excuse my dear Aunt Sally," where the first letters of each of those words is a hint to the order in which you want to do problems that have multiple mathematical operations. And it's important to do problems in the order that's listed here, because you may get a different answer if you don't. And if you get a different answer, obviously one is right, one is wrong. Somebody along the way has decided that this order that's listed on this slide is correct. So you always want to do, starting with the P, or the P in please. Some people also learn this as PEMDAS, which again is simply the first letter for each of these instructions. P, or please, stands for parentheses or any other groupings. You always do those first, beginning with the innermost parentheses, and you work in to out, innermost parentheses first, and then work out if there's more than one set of groupings, and we'll show you an example of that in just a minute. After you clear out any parentheses using whatever techniques you need to do that, then the next thing you're going to do is exponents or roots. Now, in this class, we don't do any root work, so that's not something you have to worry about, but exponents we will look at, and so that's something that you need to be aware of. After you do parentheses and exponents, then the next thing you're going to do is multiplication and division. Now, that does not mean that multiplication always comes before division. Instead, what it means is, if you have both multiplication and division, you will always work left to right in solving that particular steps of the expression. So if division happens to be farther to the left than the multiplication step, you will do the division step first. So multiplication and division working left to right if you have both. After you've done all three of those steps, then the very last thing you always do when simplifying expressions with multiple operations is you're going to do addition and subtraction. And again, just like with multiplication and division, you don't necessarily do addition first. Instead, you look at the problem left to right, and you will do whichever operation comes first as you look at the problem left to right. So if there's a subtraction problem farther to the left than addition, you'll do subtraction first. Okay, so addition and subtraction work left to right. All right, so let's do some examples just to get everybody back up to speed with orders of operation. Starting with this first example, up in the upper left-hand corner, we've got two operations. We've got addition and we've got multiplication. Multiplication is higher on the food chain than addition, so we will do the multiplication step first. 9 times 4 is 36. So now we've got 8 plus 36. The addition step is the last thing we have to do, and so we'll do that addition as our final step. 8 plus 36 is 44, and that's your final answer there. Working to the right then, notice that in the example in the upper right, we have several things going on. We have multiple operations. We also have groups. So we're going to look at the grouping symbol first, everything in the group. Within the group, there are two operations. There is multiplication and there's subtraction. So the first thing you do, because multiplication is higher on the food chain, is you're going to do the multiplication step. 3 times 4 is 12. And then also in the parentheses is that subtraction step. So we'll do that next because you always do parentheses first until you can't do anything more. 12 minus 1 is 11. And so now we have, because we haven't done the other operations, we've got 5 plus 2. Okay, now that 2 is being multiplied to that group, so I'm going to put in a multiplication dot. You can leave the parentheses in there if you want to. 2 times 11 plus 8. Now we have addition steps and one multiplication step. Multiplication comes before addition. So now we've got 2 times 11 is 22. So 5 plus 22 plus 8. Now we have two addition operations working left to right. We'll do the left one first. 5 plus 22 is 27. And then bring down the plus 8, which we haven't done yet. That's the last thing left. 27 plus 8 is 35. Okay, working in the lower left-hand corner, notice that we have two sets of parentheses. We've got the inner parentheses, and then we've got the outer brackets. If you have more than one set of parentheses, and they're nested one inside another, you always work inside out. So we're going to do this inner parenthesis first. Again, just like the previous problem, we've got multiplication and subtraction. So you will do the multiplication step first. 3 times 6 is 18. Then still, sticking with that same parenthesis, you completely finish that parenthesis work before you work outside that group. 18 minus 10 is 8. So now we have, if we rewrite the problem, 5 times the bracket group, 10 plus 2. That 2 is being multiplied to the group of what we just simplified, so it'll be 2 times 8. And then we haven't finished the outer bracket yet, although we did finish that inner parenthesis. Now inside that outer bracket, again, that's a grouping, so that's the first thing you do. You have addition and multiplication. We're going to do the multiplication step first. 2 times 8 is 16. So now in that bracket group, we've got 10 plus 16. 10 plus 16 is 26. That group is being multiplied to the 5 that is on the outside of it. And 5 times 26, which is your last step, will give us 130, I believe. Okay, moving over to the fourth and final example on this page. We don't have any groupings, but we do have exponents, which is the second thing on our list. Remember, it's please, excuse, my dear, Aunt Sally. Parentheses, exponents, multiplication and division, addition and subtraction. So we don't have any parentheses, but we do have exponents. Since we have more than one exponent in the problem, we're going to work left to right. That's always the rule. Okay? If you're on the same level, you always work left to right. So 3 to the 4th. 3 to the 4th is 3 multiplied by itself 4 times. So 3 times 3 is 9, times 3 is 27, times another 3 is 81. 4 squared, that's 4 times 4, that's 16. 2 cubed, 2 times 2 times 2 gives you 8. And 5 squared, 5 times 5 is 25. And then we're going to carry down the operations that we haven't done. The connector between the 81 and the 16 is addition. The operation between 16 and 8 is division, and I'm going to write it as a traditional division symbol. That's supposed to be division there. And then between the 8 and the 25 is subtraction. So we have addition, division, and subtraction. We want to do the division step first because it's higher on the food chain than either addition or subtraction. So 16 divided by 8 is 2. So now we have 81 plus 2 minus 25. Now we have addition and subtraction. They are equal weight, so working left to right. We're going to do the addition step first. 81 plus 2 is 83. And then that leaves us with the final step of minus 25. 83 minus 25 gives us a final answer of 58. Okay, So we're going to move on to evaluating a variable expression. Remember, an expression does not have an equal sign. So to evaluate a variable expression, you simply replace the variable, or variables if there's more than one, in the expression with the given number and simplify. For example, let's say that you are doing homework and you're asked to evaluate the expression 3a minus b when a is equal to 7 and b is equal to 5. So we're going to take that value for a and put it in for a. We're going to take that 5, put it in for b in the expression. Everything else stays the same. All the other operations remain the same. So we've got 3 times a, which is 7, minus b, which is 5, and I didn't put that in, so I will. 3 times 7 minus 5. Now it's an orders of operation problem. So the first step we're going to do is we're going to do the multiplication step. 3 times 7 is 21, minus 5, which is our last operation with orders of operation, and 21 minus 5 gives us a final answer of 16. Another example. Evaluate the expression x squared plus 2x minus 1. Let me rewrite that since I wrote over my question. Evaluate the expression x squared plus 2x minus 1 when x is equal to negative 2. All right, we're going to put that negative 2 in for all the places where x appears, which is going to give us, in this case, negative 2, both the negative and the 2 will be squared because that's what x is, plus 2 times negative 2 minus 1. Now it becomes an orders of operation problem. Do the exponents first. Now you might notice that there are grouping symbols there. There are parentheses because I used that to indicate multiplication. But in this case, there's nothing to do inside the parentheses. So therefore, the parentheses are just holding the number to do the next operation. There's nothing to simplify within the parentheses. And so therefore, we will move on from parentheses to exponents. So negative 2 squared, negative 2 times negative 2 is a positive 4 plus 2 times negative 2 minus 1. We did our exponent. Now we have 3 different operations. We've got addition, we've got multiplication, and we've got subtraction. Multiplication is the next step that you do according to operations, orders of operation. So we've got 4 plus 2 times negative 2 is negative 4 minus 1. Working left to right because addition and subtraction are equivalent. 4 plus negative 4 is 0. And 0 minus 1 gives us a final answer of negative 1. So to evaluate a variable expression, you simply plug the numbers in for the appropriate variables and use orders of operation to simplify as far as you can go. Solutions of equations. All right, the difference between an expression and an equation, as we said before, is that an equation has an equal sign. Okay? So what we're interested in doing now is finding solutions of equations, but first we have to talk about the types of equations we have. There are 2 types of equations in math, and they are this. There are true equations, like, for example, 5 plus 3 equals 8, and there are false equations. And an example of that might be 5 plus 3 equals 12. Both of those are considered equations because they have an equal sign. So they're both equations, but one is true and the other is false. And some equations may be both true and or false, depending. And here's an example of that. Let's say that I gave you this equation, 3x plus 1 equals 10. Now, if I said to you, is that equation true or false? Unless I told you what x was, you couldn't answer that equation. Because if, for example, I told you that x was equal to 3, then this equation would be true. Because if you put 3 in for your x, you'd get 3 times 3 plus 1. And the question is that equal to 10? In order to be true, those two sides would have to be the same number. Orders of operation, 3 times 3 is 9. And if you add 1 to that, you do get 10. 10 is equal to 10. True statement. So in this case, this equation is true if x is equal to 3. However, if I said to you x was equal to 1, then if you took the equation and you put 1 in for your x, you'd get this equation. 3 times 1 plus 1 equals 10. 3 times 1 is 3, plus 1 equals 10. 3 plus 1 is 4, and 4 is not equal to 10. So in this case, you would agree with me that this is a false equation. The two sides are not equal. And so in that case, same equation. Notice we used the same equation for both of these. 3x plus 1 equals 10 is true if x is 3, but it's false if, for example, x is 1. All right, so if a number makes an equation with a variable into a true equation, then that number is a solution of the equation. If we look at the previous example then, you would agree with me that x equals 3 is a solution to the equation, because when we plugged it in, we got a true statement. But on the other hand, x equals 1 is not a solution, because we got a false statement when we put that particular value in. So let's say you were doing a problem like this. The question is 6 a solution to the equation 2s minus 1 equals 7? What they're telling you there is to let whatever the variable is, in this case it's an s, let s equal 6, plug that in to the equation that they give you, and see if you get a true statement. So if we do that, we've got 2 times s, or 2 times 6, minus 1 equals 7, which is 12 minus 1 equals 7. 12 minus 1 is 11. 11 is not equal to 7. That's a false statement. And therefore, the answer to this is 6 a solution? No, 6 is not a solution to that particular equation. Okay, so let's talk about translating words into symbols. This, of course, brings up the biggest battle students face, which is the dreaded story problems or applications. And the biggest battle students face with story problems or applications is knowing what words represent in terms of mathematical symbols. It's hard for students to take the words and write it in terms of a mathematical expression or equation. And unfortunately, there are particular words that you just have to know and memorize in order to get through most story problems. So this chart gives you some of the most common keywords that indicate the 4 basic mathematical operations: addition, subtraction, multiplication, and division, and then the words that indicate that you have an equal sign or an equality that you're setting up. So you've got addition, subtraction, multiplication, division, and equalities. You need to know the keywords. For example, add always means addition. Sum also means addition. Minus means subtraction. Some of them are very straightforward. Some of them are not. And so this is a slide that you want to take good notes on and memorize them before you try to do the application problems. in your homework or in getting ready for a test. Okay, so in addition to the keywords, you also need to be familiar with the symbols commonly used in algebra for the 4 basic operations. Addition, subtraction, and equality or equals are pretty consistent and standard. But there's a wide variety of symbols used for multiplication and division. We've already looked at some of those in the order of operations problems we've done, but now we're going to formally review them. Let's start with multiplication. And we're going to start with multiplication with 2 constants. When you were originally in elementary school and you were learning multiplication, you almost certainly were taught the crossbar symbol for multiplication. For example, 5 times 3 had that crossbar symbol, but you can see in algebra that's a problem because that looks a whole lot like the variable x. And so students, when they use that symbol, a lot of times say, well, is that multiplication or is that a variable? So that's a problem. So another very traditional symbol used for multiplication is the multiplication dot, okay? Replacing that crossbar symbol. You can also take multiplication and use parentheses to enclose either the second factor in the multiplication problem or the first factor, or you could use parentheses for both factors. Now, the key here to recognizing that this is multiplication is notice that nothing else is written in between the numbers. If nothing else is written between numbers or numbers and variables, then it's understood multiplication. Okay? Now, the only thing that you can't do for multiplication is you can't just write the numbers down with nothing in between and expect a person to know that's multiplication if those are constants, because that, of course, looks to anybody who doesn't know what you're doing like 53 and not 5 times 3, and there's no way they can know that. Now let's look at multiplication with variables. Could you take 2 variables, I'm going to use a and b here, and use the multiplication crossbar? Well, yes, you could, but again, students are unsure whether that's a times b or if that's a variable and it means a times x times b. So that's a problem and not a good way in algebra to represent multiplication. You can use the multiplication dot, a times b. You could enclose the second factor in parentheses. You could enclose the first factor in parentheses. Or you could enclose both in parentheses. That's all multiplication. And when you have variables or a combination of constants and variables, you also can just write the factors down one right after another with nothing written in between them. And if nothing else is written, that is understood multiplication. So notice the difference between these two. When you have 2 variables, or if you had a constant and a variable, writing nothing between is still multiplication, but with 2 constants, that doesn't work because it looks like a different number. Obviously a problem. Okay, division. Let's look at division. The traditional symbolism for division is the division symbol, 12 divided by 6. Another very common representation is the slash symbol, which came into popularity with typewriters, and then of course now computers. Fractions, you need to remember that fractions also is division. When you write a number as a fraction, that fraction bar technically is division. Okay? So fractions are division, and then there is the traditional long division symbol. We don't use that much in here, but that also means division. With variables, same kind of symbolism. You've got the traditional division symbol. You can use the slash symbol to represent division. Fractions also can be written as division, and then you can write your variables with long division, which sometimes is helpful, especially in the higher level algebras and beyond. Long division is sometimes applicable. Okay, so if you are unfamiliar with any of that multiplication or division symbolism, that's something that you want to get clear in your head. Inequalities. There are 4 basic inequalities that we're going to look at. There is less than, which is the arrow pointing to the left. There is less than or equal to. There is greater than, or there is greater than or equal to. Examples of their use might be something like 3 is less than 5. You would agree with me that the quantity 3 is less than 5. Less than points to the left. Less than or equal to also points to the left. 4 is less than or equal to 6. That's also a true statement. Watch out for these. 5 is less than or equal to 5. That also is true. Often students will say, well, no, that's false because 5 is not less than 5. That's true. 5 is not less than 5, but it is equal to 5. And when you're using the less than or equal to or the greater than or equal to, the key word is or. It doesn't have to be both. It just has to be one or the other. So although the 5 is not less than 5, it is equal to 5, and so therefore 5 is less than or equal to 5 is a true statement. Greater than, an example of that might be 10 is greater than 3. Greater than or equal to, again, 10 is greater than or equal to 3 is a true statement. So would 3 is greater than 3. That's also true. Again, it doesn't have to be both. It just has to be one or the other. And if you are rusty on those inequalities, that's something you want to review as well. Okay, so let's put all of that together with some examples. The problem would say something like this. Translate the following into an algebraic expression or equation where appropriate. Use x to represent any unknown value. So x is going to be your variable. First example, the product of 8 and a number. Okay, now this turns out to be an expression because there's not a key word that indicates an equality or an equal sign. So what you want to do is you want to look for key words from that previous slide where there was a list of key words for the 4 basic operations and for equalities. So the first keyword that jumps out at me is the word product. I know that product in math always means multiplication. So product means multiplication, and if you're multiplying something, you have to know what you're multiplying. So that almost always is the next 2 things that are mentioned. Okay? The product or multiplication of 8, so 8 is the one thing that's being multiplied, and a number, okay, they don't tell you what the number is, so that's your unknown value. We're going to let that be represented with x because that's what the problem says to do. And so the product of 8 and a number would be 8 times x. And you're done, unless, of course, you want to just write it as 8x without the multiplication dot. Remember, if we have a constant and a variable combined with multiplication, you can leave it without anything written in between, and it's understood multiplication. Okay, next problem. The quotient of a number and -5. Again, look for keywords. The key word here is quotient. Quotient means division. Okay? So in this case, we're going to be dividing 2 numbers, but order is important. With multiplication, order isn't important because multiplication is commutative. It doesn't matter whether you multiply, say, 5 times 3, that's the same as 3 times 5. So order is not important. But with division, you would agree with me that 12 divided by 6, which is 2, is not the same as 6 divided by 12, which is, if you write that as a fraction, 1/2. Okay, so order is important. With division, usually you just assume that the order that they list the factors that they're dividing is the order that you will write them as well. So this says the quotient, which means division, of a number. Okay, they don't tell you what the number is, so we're going to let that be x, and negative 5. So going in that order, division, the quotient of a number, which is x, and negative 5. That's one way you could write that problem. If you wanted to use a different symbol, you could. You could use the slash symbol, or if you wanted to write it as a fraction, that would be fine as well. Another example, 5 times a number decreased by 34. Okay, reading left to right. The word times here indicates multiplication. We're multiplying 5 times a number. Okay, again, that's an unknown number, so it'll be x. Okay, 5 times a number decreased. Okay, so that product then decreased. Decreased by means subtraction. That's a key word. 34. Or to clean it up, 5x minus 34. 5 times a number minus 34. And one more on here. I apologize for writing over that problem. It says 4 added to a number is equal to 39. Okay, so reading left to right, we've got 4, of course, is a number. Added always means addition. That's a straightforward keyword. Added to what? Added to a number. Again, that's our variable, x, is equal to. Okay, now this is different from the previous problems because this actually is an equation. Equal to is a pretty straightforward key phrase for equals. And what's it equal to? It's equal to 39. So 4 added to a number is equal to 39. Another example. A number decreased by 12 is less than or equal to 8. Now in this case, this is going to be an inequality. Okay? So reading left to right, a number would be x, decreased by, those are keywords for subtraction off of that chart. Decreased by what? Well, decreased by 12. So x minus 12 is less than or equal to. This is why we reviewed inequalities. The symbol for less than or equal to is an arrow pointing to the left, and then it has that equals portion as well. Is less than or equal to what? 8. "24 added to twice a number is 34. Again, look for key words. Added means addition. In order to add things, you have to have two things to add. Okay, so in this case, it says 24 is added to. Now be careful here. We've got that number, which of course is x. Okay, but twice a number, that's a key word for multiplication, but a specific type of multiplication. Twice a number means 2 times. So we're adding 24 and twice a number, which is 2x, or 24 plus 2x, is a key word for equals. It's an equality. And it's equal to what? That's the last thing in the sentence, 34. So to clean that up, 24 plus 2 times x, or just 2x, is equal to 34. Next example, the sum of a and b is greater than 5. Sum, keyword for addition. What are we adding? It's usually the next two things in the list. We're adding a and b. And that is greater than, okay, that's an inequality, is greater than, it's an arrow pointing to the right, is greater than what? It's greater than 5. The ratio of 3 times a number and 3 gives 4. Okay, ratio. Ratio is a key word for division. Okay, but usually ratio is more accepted if the division is written as a fraction. So I'm going to write it as a fraction, but recognize it is division, so if you use the division symbol, that wouldn't be wrong. Okay? But I'm going to use a fraction to represent my ratio. Okay, so division, what are we dividing? We're dividing 3 times a number. Okay, times means multiplication. 3 times means 3 times. 3 times what? A number, that's our variable. Okay? So the ratio of 3 times a number, that would be 3x, and 3, so that's our denominator, okay, gives. Gives is a key word for equals. Gives what? It gives 4. 3x divided by 3 equals 4. Okay, so this is the end of Module 6, Section 1.3 material. You should now complete the homework for Section 1.3, which is found in MyMathLab. And when you have successfully completed Section 1.3 homework, you want to proceed to the next video in the series, which is Module 6, Section 1.8.